All right. Welcome to the Condensed Matter seminar today. And sorry for the delay. It's my pleasure to introduce our speaker today, Professor Joe Sklenar. Joe is a Case alumnus. He obtained his BS in physics from Case in 2009, and Professor Cash was his senior project advisor. He then received a PhD from Northwestern in 2015 under the supervision of John Katzen. During his later years in grad school, he was also worked with Axel Hoffman at Argonne National Lab on magnetization dynamics in heterostructures. And the first time I met Joe was in Argonne, actually. And he gave me a lab tour. And that was a memorable experience for me. Nothing was damaged. Okay. And Joe also won the GMAG Outstanding Dissertation in Magnetism Award in 2016. Before he joined the Department of Physics at Wayne State, Joe did one postdoc at the University of Illinois at Urbana-Champaign with Peter Schiffer and Nadia Mason on artificial spin ice, as well as spin transporting antiferromagnetic materials. And today, Joe will tell us about his recent work on hybridization of magnons in antiferromagnetic systems. Without further ado, Joe, please.
Thanks, Shulei. So it's really nice to be here today. I'm used to anything else said. I'm here to tell you about self-hybridization and tunable Magnon-Magnon interactions in layered antiferromagnets. This is the first time I've been back at Case since I graduated with my bachelor's degree, so it's special for me. Also, it's the first time I presented results that are from my group just at Wayne State, not from my postdoc period. So I joined Wayne in the fall of 2019, and this is the topic that I'm going to talk about today. The picture in the back, I might need to mute my computer. Maybe I'll mute it.
Yeah.
What about you when you mute yours?
Okay. Should I just proceed?
Well, is yours muted?
Yeah, this is muted. Oh, no, sorry.
There we go. Okay, cool. So, if this was pre-pandemic, this is the topic that I'd probably tell you about. And I just put this slide up because it's something that you can ask me about later while I'm visiting. It's another area that I'm interested in, artificial spin systems. And it's a fun topic to talk about because it's so visual. So these are nanomagnets that behave like Ising spin systems artificially on a chip. And so we study in my group phase transitions engineered into these magnetic nanostructures through nanostructuring. So it's not the topic of my talk today, but I flash it up there just in case it might invite conversation later. What I'm going to talk about today is more in the mainstream of magnetism these days in spintronics. So it's involving magnetization dynamics of antiferromagnets. So the outline of my talk is as follows. I'm going to help motivate some of the recent interest in antiferromagnetic materials with a brief introduction into magnetization dynamics. Then I'll talk about what we did during the pandemic, which was modeling Magnon-Magnon interactions in layered ferromagnets with micromagnetic simulations and with some macrospin models. Then at the end of my talk, I will talk about some of our recent experimental realizations of synthetic antiferromagnets that have these self-hybridization effects that I will talk about in the modeling part of my talk. So just one quick slide about antiferromagnetism, if you're unfamiliar. So this was a magnetic ordered phase of matter that was predicted by Nile, who won the Nobel Prize for it in 1970. And he kind of famously said during his Nobel Prize lecture that at the time, they do not seem to have any applications, even though they are extremely interesting from a theoretical viewpoint. And things have changed since then. So these are materials where there is magnetic order, but you do not have a net magnetization. This is an example of an antiferromagnetic material, iron rhodium. The orange spheres represent iron atoms. The blue body-centered sphere represents a rhodium atom. And in this material, there's a low temperature antiferromagnetic phase where the magnetic moments on all of the iron sites tends to be anti-aligned through the exchange interaction with the neighbors. Another example of an antiferromagnetic material that is relevant to my talk today is shown on the lower right, chromium trichloride. This is actually a van der Waals magnetic material, so you can exfoliate it. You can think of chromium trichloride as having layers that have ferromagnetic interactions within a layer, but there are antiferromagnetic interactions between the layers so that there's still no net magnetization. But again, there is magnetic order. Okay, so aside from in the 1990s, antiferromagnetism became important from the perspective of magnetic memory storage because antiferromagnets were used as a passive role with the exchange bias effect. Aside from that, like really huge development, there wasn't much interest in using antiferromagnetic materials for active applications until somewhat more recently. So in 2016, the group of Thomas Youngworth actually showed that you could electrically switch the magnetic memory state in an antiferromagnetic metal. So the material that they were using is copper manganese arsenide. If you look at the lower left, you see a memory device that they fabricated. This cross-like structure is the copper manganese arsenide that's patterned into a device. Basically, by passing current up and down, left and right, they could electrically switch antiferromagnetic domain states within the cross, and they could read out a magnetoresistance along the diagonal leads that would be sensitive to the magnetic domains that are within the cross-like structure. So this was all possible because this particular material has an intrinsic spin orbit torque where if you have a current passing through the material, there is a torque on the antiferromagnetic moments. That's a little outside the scope of my talk, but this research really invited many other people to start to think about how to come up with active uses for antiferromagnets. And although this device is far from being an ideal memory, it demonstrated that you could, in fact, electrically control some property of an antiferromagnet. So I'm interested in magnetization dynamics, and one of the reasons why people are interested in perhaps making a magnetic memory out of an antiferromagnet is because of the magnetization dynamics. And the cartoon on the lower left, this is an illustration of antiferromagnetic resonance, or I'll use these words interchangeably, an antiferromagnetic magnon, where you have two antiferromagnetic moments, Ma and Mb. There is an external magnetic field, and due to an antiferromagnetic exchange coupling, they tend to want to be anti-aligned, but they can rotate towards the external field. I'm illustrating precession of these two magnetic moments around an effective field direction that they would relax to in equilibrium. And antiferromagnets, unlike ferromagnets, will tend to precess at much higher frequencies due to the strength of the exchange interaction between the two magnetic moments. So these antiferromagnetic magnons, or this antiferromagnetic resonance process, can occur with precession rates at terahertz speeds, sub-terahertz speeds, and gigahertz frequencies as well. Ferromagnets tend to precess at gigahertz frequencies. So if you're thinking about writing information into a ferromagnetic memory, your switching rate is usually of the order of nanoseconds. But if you could make an antiferromagnetic based memory, you can imagine writing information on picosecond timescales. So this is an antiferromagnetic resonance transmission spectrum from nickel oxide. And it just is a good example of an absorption of terahertz near 1 terahertz that is associated with excitation of this antiferromagnetic magnon. We also have ways of detecting these high frequency excitations electrically these days. This is a technique that was inspired by work that was done with ferromagnetic spintronics. Basically, if you take an antiferromagnetic material and if you deposit, say, platinum, tantalum, tungsten, these materials with strong spin orbit coupling on top of them, if you can generate antiferromagnetic resonance in the antiferromagnet, a process called spin pumping will allow a spin current to be injected from the antiferromagnet through the interface into, say, the platinum layer, which can then be electrically detected through a process that happens in the platinum known as the inverse spin Hall effect. So this is very interesting because you can electrically detect this antiferromagnetic resonance at 240 gigahertz here by simply measuring the voltage across the platinum layer that's on top of the antiferromagnet and sweeping the field to the resonance condition. So if you'd like to learn about more of the sort of broad trends in antiferromagnetic metals and antiferromagnetic spintronics devices, I would point you to a review that we recently wrote. This is sort of the big picture motivation that I wanted to talk about. But now, before I can get into the details of our work, I probably should take a step back and review magnetization dynamics in general. So the equation of motion that describes how magnetization processes around an effective magnetic field direction is known as the Landau-Lifshitz-Gilbert equation. Here, the rate of change of the magnetization with respect to time goes as the cross product of the magnetization with an effective magnetic field. And the second term, alpha m cross dm dt, describes how the magnetization, if it's perturbed from the effective field direction where it resides in equilibrium, tends to relax as it processes and sort of spirals around the magnetic field direction. The effective fields that can be used to, that you can model with this Landau-Lifshitz-Gilbert equation can be external fields, demagnetization fields from the shape of your sample or specimen, or exchange interactions, magnetocrystalline anisotropies, etc. So you can actually take two of these Landau-Lifshitz-Gilbert equations and couple them together to come up with a really simple model for antiferromagnetic resonance. So this is the picture I showed earlier. You have an external field along the y direction, and you imagine that before you applied the external field, one magnetic moment is along the plus x-axis, the other is along the minus x. So the equation of motion then that you would write to describe how the magnetization evolves in time has an effective field that depends on the external field orientation. The second term in this equation of motion is the exchange field. So for instance, the exchange field that MA experiences is in the opposite direction that MB is pointing, because it's an antiferromagnetic exchange, and there's some effective field strength, HE, that it's the magnitude of the exchange field. The third term in the equation of motion is the demagnetization field from basically assuming that these magnetic moments are living in a very thin film. So the systems that we study that I'll show you basically do have shape anisotropy. They're films that are maybe tens of nanometers thick in the Z direction, and they're, for all intents and purposes, continuous in the XY direction. Yeah.
Is it supposed to be a vector?
The MA.Z, oh, I am missing a Z hat. Thank you. Yeah, when I typed up those equations. Yeah, the final term is a demagnetization field from, if the magnetization tilts out of plane, there should be a field that restores it back into the plane. So in the minus Z direction. That's why there's a minus MS, where MS is the saturation magnetization. Good catch, it's a typo. So if you linearize these equations of motion, you can find two solutions that describe the antiferromagnetic resonance. One solution is illustrated here. The way that I'd like you to think about it is you have MA and MB processing around their effective fields. When MB rotates towards the Y direction where the external field is oriented, MA rotates away from it. So they're bending one will bend towards the external field, one will bend away as they process. We call this the acoustic antiferromagnetic resonance. It's linear in the external field, and the equation for it is shown on the upper right. The plot is, you can also determine these numerically through methods that I will discuss in this talk. So the color map is also showing the acoustic Magnon mode trajectory. There's another solution to these coupled LLG equations that we call the optical antiferromagnetic resonance. So here, MA and MB, as they process around their effective field directions, they bend towards the external magnetic field and away, and towards and away. This is a mode that has a finite frequency at 0 magnetic field. So actually, if you turn off your external field, the optical antiferromagnetic resonance still occurs at this, it goes as the square root of 2 times the exchange field times the magnetization. This is why you can have such high frequency antiferromagnetic magnons, because for some antiferromagnetic materials like nickel oxide, for instance, this exchange field is many tens of Tesla. And I should have mentioned this, gamma is the gyromagnetic ratio. This is a constant that's 28 gigahertz per Tesla. Sort of, it gives you an idea of what your precession rate should be for a given field strength. So if HE is large enough, you can actually have frequencies that are hundreds of gigahertz, thousands of gigahertz. Obviously, I'm showing you a picture where HE is input to only have an optical resonance frequency at 7 gigahertz. So you might be wondering why that's the case.
So
Yes.
in both cases, you fix the magnetic field in the direction that's perpendicular to the neo vector.
Yes.
Okay.
Yeah.
Your H0 is the same as your H external?
Sorry.
Is there a static and a frequency dependent H external?
Here, and that's sorry, because I drew the formula from 2 different places. H0 is H external,
Okay.
and it is a static magnetic field that you're imagining is present. And so when you linearize these equations, you guess solutions that are like, I'll have a diagram in a couple of slides, but you guess solutions where the magnetization is basically processing around with small amplitudes in the static field with an exchange interaction to present.
And you're also assuming that this nail order is uniform across the sample.
Yeah, this model here is what we call, it's a kind of macrospin model where you are assuming that the one magnetic sublattice is described by one vector MA, the other magnetic sublattice is described by another vector MB. So it doesn't capture finite wavelength Magnon excitations here. But some of the micromagnetic simulations that I'm going to describe are able to do that. Yeah, good questions. Okay, so well, it's easier to access magnons at lower frequencies because we have signal generators that are commercially available, inexpensive, that can create high power microwave signals from say 1 to 20 gigahertz. And so if you're looking to study antiferromagnetic resonance easily, you might want to think about materials that have small enough exchange interactions that bring the dynamics down to gigahertz frequencies. And van der Waals magnetic materials, 2D magnetic materials, actually have this property. So chromium triiodide was one of the first reported 2D magnets, but chromium trichloride, which is kind of akin to it, is a very interesting material from the magnetization dynamic point of view. So this is a material that has ferromagnetic interactions within a given layer and antiferromagnetic interactions between nearest neighbors. in the C along the out of plane direction. The effective interlayer exchange field for these materials is about 100 millitesla, and that's what's bringing the frequencies down to gigahertz. These materials, you can exfoliate them down to the monolayer limit, and they have these magnetic phase transitions below 20K. So for instance, this material will order into an antiferromagnetic phase below 15 Kelvin. And in 2019, Lo-Cha-Lu's group at MIT actually reported experimental antiferromagnetic resonance of chromium trichloride at these gigahertz frequencies. It's an experimental technique that's pretty standard, and I'll talk about it a little bit more at the end of the talk. Basically, you take your sample, you place it on a broadband coplanar waveguide. That's what's illustrated on the left. And the waveguide can broadcast microwaves, say from 1 to 10 gigahertz. And you're looking for absorption in the transmission of microwaves through the waveguide as you sweep, say, an external magnetic field at a fixed frequency. So this is what the antiferromagnetic resonance spectrum looks like. You can control the modes that you couple to based on the in-plane field orientation. And you see a kind of bluish blob on the panel in the middle at high frequencies, low fields that they are associating with the optical Magnon mode. And you do see a sort of bluish linear curve that is associated with the absorption of microwaves that's generating the acoustic antiferromagnetic resonance. What they also did, and this is starting to get to the core of my talk, is they rotated the external magnetic field out of plane. So the magnetization tends to want to lie in the plane due to shape anisotropy effects. But what they found after rotating the external field out of plane is that they could create an avoided energy level crossing in the spectrum of the antiferromagnetic resonance. So what's happening as they rotate the field out of plane is that they're able to hybridize the acoustic magnons with the optical magnons. Okay, I'm going to come back to that, but I also want to take this moment to introduce synthetic antiferromagnets. This is a kind of artificial antiferromagnet, if you will, where you take ferromagnetic materials like cobalt, iron, boron, you grow them with sputter deposition, for instance, and you space them with a layer like ruthenium. And based upon the thickness of the ruthenium through the RKKY interaction, you can have an antiferromagnetic coupling between two ferromagnetic layers. If you change the thickness of the ruthenium layer, you can restore ferromagnetic coupling. And then typically as you change the thickness of the ruthenium layer, you have oscillations in the effective exchange field from ferromagnet to anti, from ferro to anti between the two magnetic layers. And honestly, from the perspective of magnetization dynamics, the spectrum looks really similar. You see an optical Magnon mode and an acoustic Magnon mode in these artificial antiferromagnets.
How much do you have to change the thickness to switch from ferro to anti?
Usually the period is around, I think, 1.5 nanometers to 2 nanometers. So actually, I'm going to show you some of our own experimental results where changing the thickness from 1 to 1.25 nanometers changes the coupling from antiferromagnetic to ferromagnetic.
Okay, so I'm kind of amazed you can do this because I thought these things would be rough and it would all smear out.
So we haven't actually characterized our samples yet with like cross-sectional TEM to get a sense of the roughness, but we have calibrated sputtering rates. We'll sputter at low power. Surface roughness is definitely something that comes into play for sure, but it's sort of, people will grow a series of samples with different timings and they'll see these nice oscillations in the exchange coupling, usually growing samples with thickness changes of like 0.5 nanometer. Using synthetic antiferromagnets, you can actually get the same results that were observed with chromium trichloride at room temperature. So the van der Waal materials are nice because they're 2D materials and we think they're really cool just based on that alone. But from the Magnon-Magnon interaction perspective, you can see all of the same physics with these artificial magnets. So this is a cobalt iron boron based synthetic antiferromagnet. You can see the optical magnon, the acoustic magnon branch, and as the field is rotated out of plane, it basically reproduces the same physical effects that were seen in the layered antiferromagnets.
And that's at room temperature?
This is at room temperature, yeah. So we do all of our microwave spectroscopy measurements at room temperature, which is great if you're thinking about devices, right? There are disadvantages. I mean, well, you know.
What are the axes here? The axis, the x-axis is the field.
So you're imagining there's an external field that is rotating from the y direction to the z direction out of plane. And maybe your Nile order is initially initialized so that the moments are staggered along the plus and minus x direction. So I'm not illustrating the canting out of plane, but they are presumably canting out of plane to a new equilibrium position. Yeah.
Okay. And then you're scanning a magnetic field and
this sample is still on something like a waveguide. You're fixing a frequency of excitation, I suppose. So like you have a driving RF field at 3 gigahertz, you sweep the magnetic field and you look for absorption in the transmission of the microwave signal as a function of your field that you see.
So the hybridization is maximized when the field is out of plane for sure, but
The maximum is probably at some arbitrary angle in between, because I think if you go fully out of plane,
yeah.
well, I don't think that there will, I have to think about what the modes look like, but I don't think that there will be a coupling between the modes. You need some symmetry breaking out of plane field.
Yeah.
But people are starting to get clever. There's other ways to couple acoustic magnons with optical magnons. One way is to not excite a uniform antiferromagnetic resonance, but a spatially varying antiferromagnetic resonance. So a finite wave number, magnon, if you will. So the blue box is your synthetic antiferromagnet. You pattern a microwave antenna on top of it. That's going to generate an exciting field that has some spatial inhomogeneity. So you couple to a magnon, an acoustic or an optical magnon, where the precession varies across some length scale lambda. And so this is still an acoustic-like and an optical-like antiferromagnetic resonance, and they still share similar frequencies as the ones that I've described so far, but now actually they're able to interact through the dipolar interaction. So in this measurement here, when the external magnetic field is along 45 degrees from the wave number, you can see a faint little avoided energy level crossing opening up between the acoustic and the optical mode. Okay, so I'm going to pause because I feel like some of this is a little disingenuous, because I started off with a motivation about terahertz, and okay, now I'm talking about gigahertz antiferromagnets. So why, okay, it's nice to study these materials because it's easier to access the modes at gigahertz frequencies. We do think that ideas can be validated on these systems, sort of as test beds that we'd like to transfer down the line to higher frequency antiferromagnetic materials. And already there are people thinking about functionalities, applications of these synthetic antiferromagnets at gigahertz frequencies. So for instance, if you can tune the magnon-magnon interaction in a very agile way, maybe you have things like frequency filters in the 1 to 30 gigahertz range that could be useful for like wireless communication technologies. So there's people actually at the Dayton Air Force Base that are interested in these types of technologies. I'm citing a paper here that you can read a little bit more about some of those motivations. I also want to mention that there is a growing field in magnetism called hybrid magnonics, which is actually living at the gigahertz frequency range, where people are interested in studying fundamental physics involving strong coupling between magnons and other quasi-particles like photons, phonons, and other magnons. There's an excellent review article here written by a friend of mine that sort of explains why we're interested in hybrid magnonic systems, but the eventual goal is, for instance, to maybe transduce signals from one quasi-particle to another to maybe aid in the engineering of really complex hybrid quantum systems like a Magnon photon qubit. So if you can read out information from a Magnon that's coupled through a photon to a qubit, maybe you have something useful. But that's some far-reaching applications that I'm not going to spend time talking about now. Okay, so I hope I kind of convinced you that gigahertz antiferromagnetic resonance is interesting. And now I'd like to start to talk about our work. And to introduce it, I want to ask a simple question, which is basically, why does this model work well to describe the acoustic and anti-optical magnons in the first place? So the synthetic antiferromagnets that are typically studied are composed of two layers. So it makes sense then that you would use and equate two coupled magnetic moments in your equations of motion. But if you have something like chromium trichloride, and this is what it looks like, you have many, many layers. So you really are representing one entire magnetic sublattice with Na and another entire sublattice with Mb. But people are interested in exfoliating these materials down to the monolayer limit anyways. And along the way, you'll end up with things like trilayers, tetralayers, bilayers, hex layers. So I started to think about this question here: how sensitive is the Magnon spectrum towards the number of layers in your system? And so you can imagine on the left, this is a tetralayer of chromium trichloride, but you can make a synthetic antiferromagnet that's a tetralayer too, just by sputtering multiple layers of your ferromagnet and ruthenium, your spacer. And that was the original question that I was interested in. And then as the work kind of went on, I started to ask the question if there are new types of Magnon-Magnon interactions in these finite layer systems. So this was during the lockdown, and if you're going to,
So I have a quick question.
yeah.
So this is already pretty much a 2D system, right? In a single layer.
Mhm.
And there's this Wigner theorem saying that no long range order in the 2D magnet. So this material has a very strong anisotropy or something like that.
So chromium triiodide has strong anisotropy. It's like an Ising system.
Yeah.
Chromium trichloride. So it's a good question whether or not you have ferromagnetism in a monolayer of chromium
Well,
trichloride.
if you have anisotropy, probably you can.
Yeah.
That's a different story.
I think that there is very weak in-plane, though, magnetocrystalline anisotropy within these materials. Unlike chromium triiodide, that was what was observed to be ferromagnetic in the monolayer limit. It's like a 2D Ising system. I think that's how people think about it. Although, to be honest, Shulei, I don't know if someone has looked at a monolayer chromium trichloride and verified that it's ferromagnetic. I know that bilayers are antiferromagnetic, though.
Yeah. Okay.
So I guess it depends on whether it's Ising-like or easy plane, right? And if it's easy plane, then I guess the problem you're raising Shulei would be there. But if it's Ising-like, it would be okay.
And this one's not Ising-like.
All right.
Yeah. But bilayers are antiferromagnetic.
Is it easy plane?
There might be some in-plane magnetocrystalline anisotropy, but when I study it, and when you look at the bulk chromium trichloride and you look at the antiferromagnetic resonance spectrum, there's no real evidence for strong in-plane anisotropy. Okay, let me know how I'm doing on time. I know we started late. So my lab was closed down because of COVID, and we don't have to talk about COVID. So we started to model these materials two different ways. So this was a way to pass time, but actually it turned into something that became quite interesting to me. You can build models that I call macrospin models that are basically the coupled LLG equations. And then you can linearize them, solve the eigenvalue problem to calculate the eigenfrequencies. Another technique that I use, and I'm going to give a short tutorial on it, involves micromagnetic simulations. So there's freely available software like Mumax 3 that only requires a single NVIDIA like GPU card to run on your desktop machine that are quite powerful these days. This ellipse is a micromagnetic object that's 200 nanometers long, 80 nanometers wide. And you can see that actually you discretize the ellipse into volumes that house microspins that each individually obey the Landau-Lifshitz-Gilbert equation with all the interactions that you can possibly throw in. So I built 4 of these, stack them on top of one another, and put in an antiferromagnetic exchange coupling between the layers. And this is another tool that you can use to calculate antiferromagnetic resonance in a micromagnetic object. So I'm going to start with the Macrospin model. It's pretty much similar to what I showed earlier. You write down 4 copies of the LLG equation, except you note that the layers on the surface are only coupled to one layer. A is only coupled to B, but the layers on the interior, like B and C, are exchange coupled to the layers above and below them. So if you look at the equations of motion, you'll actually see that, for instance, in the dm B dt, there is an exchange coupling between B and A and B and C. So also the static equilibrium orientation, as this picture illustrates, is different amongst each of the layers because they each feel a different effective magnetic field. If you linearize these equations of motion, the eigenvalue problem ends up looking like the determinant of a 4x4 matrix. This is the equation that you come up with. It's messy. I just show it here for posterity, but you can solve this equation numerically, and the plus and minus in this equation corresponds to the solutions for the acoustic magnons and the optical magnons. I'm happy to describe the details of how I solve these equations later, but I'll move on. Another way that you can calculate the magnon modes is to use these micromagnetic simulations. So this is just an illustration, but I would like to tell you how we do this. You start with 2 moments or 4 moments, but I'm illustrating it with 2, that are aligned, say, along the plus or minus x axis. You apply an external magnetic field, say, along the y-axis, let the system relax into a new equilibrium position, these micromagnetic objects. Then you can apply a field pulse in the, say, y direction along the external field. That's going to excite optical modes. Or you can apply a field pulse short in time along the z direction, and this is going to excite the acoustic modes. At the end of all of that micromagnetic protocol, you end up with a time series. You can take the average of the magnetization of the entire object and plot it as a function of time after the field pulse. So here I'm plotting the y component of the magnetization after the system was kicked with the field in the y direction. After the pulse, it oscillates due to the magnetization precessing and relaxing. You simply take a Fourier transform of this time series, and that's the Magnon spectrum. So here's the results for the optical magnons in the tetra layer. You see that there's not 1 branch, but 2 branches, which sort of makes sense when you think about how the surfaces are going to be different from the inside. The macrospin results are on the right. The micromagnetic results are on the left. Red color means there's a peak in the Fourier amplitude. Blue color means there's no peak. Black contours are just the eigenvalues. And what you see is that there's an avoided energy level crossing between these 2 optical branches. That is implying that these 2 optical magnons are interacting with one another as you increase the magnetic field. This is what we call self-hybridization. It's a new interaction between optical magnons, I suppose. This is what the acoustic spectrum looks like. And again, the Macrospin model and the micromagnetic simulations are agreeing pretty well with one another, even though these are nanomagnets that we're studying in micromagnetics, which is maybe a little surprising. You see a low frequency branch that is linear, and a higher frequency acoustic branch that is flatter, and as you increase the field, they tend to bend away from one another. So it looks like there is maybe an interaction between these acoustic magnets. One nice thing that you can do with micromagnetic simulations is you can actually spatially resolve where the magnetization is precessing with high intensity. So you can, say, apply a magnetic field like 500 Ørsted, hit the system with the field pulse, but record a time series for every micromagnetic pixel in your simulation. Then you fast Fourier transform every single micromagnetic pixels time series, and you come up with these maps. So you can actually see that the low frequency mode here at 500 Ørsted lives at 5.1 gigahertz and it resides on the surface layers. At 8.9 gigahertz, that's the high frequency mode. This is an optical magnon that's living on the interior layers. As you increase the frequency towards, increase the field towards the avoided energy level crossing, you'll actually see that the amplitude is more democratic across all layers. This is where the modes are most strongly interacting. So the low frequency mode still tends to live on the surfaces, but there's appreciable amplitude on the interior layers as well. And vice versa for the high frequency mode.
But there's also like inhomogeneity in the plane. It looks like there's some, you see these color patterns.
Yeah. There are demagnetizing fields from the shape of these ellipses. And I chose ellipses because it gives me an easy access to initialize the simulations along, say, the plus and minus x direction. But then as the magnetization starts to rotate, you're right, you start to see these inhomogeneities. This is,
So it's basically like confined modes depending on your boundary condition.
yeah.
Just like the, the vibrational motion of a drum.
And it's to my mind, it's somewhat remarkable actually that the Macrospin model even sort of agrees pretty well with the micromagnetics to begin with. You also might ask the question, well, why does the if you compare these two results, why does the branch from the micromagnetic simulations look like it's extinguishing? You can't see the high frequency branch across all fields. The modes become spatially inhomogeneous in these small nanomagnets. So I'm hitting it with a uniform field pulse, but I'm actually not able to couple to it very strongly then, because things are somewhat inhomogeneous. Yeah.
So with your macro model, you don't include the boundary conditions and these finite size effects.
Right.
But with the other one you do.
We assume the Macrospin model is assuming it's basically an infinite thin film, and there's finite shape effects from the out of plane demagnetization field. Okay, so we also have identified the sort of origin of this Magnon-Magnon interaction in these systems. It's due to the dynamic part of the interlayer exchange interaction. So you can, since it's a simulation, you can do whatever you want, right? You can disable the dynamics on the surface layers or disable the dynamics on the interior layers and repeat the simulation, calculate the spectrum and overlap them. So in other words, you can keep the static part of the exchange field and divorce it from the dynamic part of the exchange field. And you just see the two branches cross one another with no avoided energy level crossing. So it's really, the interaction is happening through the dynamic part of the exchange interaction in these layered systems. So that's actually what's going to lead me to this bottom question here. The antiferromagnetic spectrum is clearly dependent on the number of magnetic layers. We've actually done 6 layers and 8 layers as well. Every time you add a new pair of layers, you get a new pair of branches in the Magnon spectrum. So the question that we then started to ask ourselves is, are there new opportunities to control the Magnon-Magnon interactions in these tetralayers, for instance, that are just not available to you in bilayers or say like the very thick chromium trichloride systems? And something that we landed on involves ideas from my past where you inject, say, a spin current from a non-magnetic metal into a ferromagnetic metal. This is a phenomenon that we call spin transfer torque. My one slide summary on this is, if you have an interface between a non-magnetic metal like platinum and a ferromagnetic metal, if you have a spin polarized current generated, say, from a spin Hall effect in platinum, and if the spin polarization is parallel to the magnetization, you will exert through a spin transfer torque a damping-like torque on the magnetization, so it will tend to relax faster. Or if you have a spin polarization that's anti-aligned to your magnetization, you will exert an anti-damping-like torque, which tends to increase the amount of time that it takes the magnetic moments to relax if they're perturbed. So this effect was originally proposed by Sloan-Zewski in '96. It's sometimes called a Sloan-Zewski spin transfer torque. And Berger also in '96 independently came to it. So this is sort of what we propose to the two-dimensional magnetism community. You imagine encapsulating your tetralayer into in some surface capping layers that has the ability to generate a damping-like torque if you pass a current through it. So you imagine J1 and J2 are current going through these red slabs that through a spin Hall effect can exert a damping-like torque or anti-damping-like torque on the A layer and the D layer. And I'll mention that you can imagine doing this with not spin Hall metals, but topological insulators like bismuth selenide or TMDs like tungsten ditelluride. These are materials that are known to generate damping-like and anti-damping-like torques on ferromagnets when they're adjacent to them. So if you can modulate the damping, the magnetic damping on the surface layers, you can control the dynamics on the surface layers and then maybe electrically manipulate the Magnon-Magnon interactions in these materials. So in simulations, for instance, we can control the damping on the two surface layers, and we can increase the damping on the two surface layers. Here I'm showing you the optical Magnon spectrum. As we increase the damping on the surfaces by a factor of 4, a factor of 10, and a factor of 1,000. And you can see that the gap between the two Magnon branches will eventually close if you dampen the surface layers. You can also imagine doing this asymmetrically. Maybe you were only interested in damping the top surface. If you do this, you actually can open a new avoided energy level crossing in the Magnon spectrum at lower frequencies by sort of asymmetrically adjusting the damping on the surfaces. So this is what we think is a viable path forward to electrically manipulating Magnon-Magnon interactions. But in my lab, we're not interested in doing this with van der Waals materials. We're interested in working with the synthetic antiferromagnets. Am I doing okay? Or
yeah.
Okay, so we have a magnetic deposition system that's actually quite versatile. There's some plasma, Kathy. it's sort of, anyways. Why are we interested in synthetic antiferromagnets? So they work at room temperature. They're easier to handle. They're not air sensitive, unlike the two-dimensional materials. We like the idea of sputtering because we can sputter ferromagnetic insulators, ferromagnetic metals, antiferromagnetic insulators, antiferromagnetic metals. We have 7 different sources in the system, so we can make lots of different types of heterostructures. And with the proper choice of materials, you can tune the interlayer coupling. And when you look at the literature, in principle, from say 3 to 40 gigahertz, the interlayer coupling can be tuned such that the optical magnon can maybe vary from 3 to 40 gigahertz. So these are like this is the first time I'm presenting experimental results from my group. My student started to work on bilayers, and so basically he's working with permalloy. It's a ferromagnetic material, a nickel iron alloy, and he's using ruthenium as a spacer layer to achieve antiferromagnetic coupling between the permalloy layers. Initially, he was using a capping layer of platinum and not necessarily putting anything on the bottom. So we're usually growing 6 to 10 nanometer thick platinum films as a capping layer. We're fixing the permalloy to be 5 nanometers, and we're varying the spacer layer, say, between 0.5 to 2.5 nanometers. And at 1.25 nanometers, you see a nice hysteresis loop, which just means that the system's behaving like a ferromagnet. With 1 nanometer spacing layer, we have this linear magnetization versus field, which is actually indicative of antiferromagnetic coupling between the two layers. When the magnetic field goes to 0, there's no net moment. It doesn't remember anything because it's behaving like an antiferromagnet. You'll notice, though, that there's a small hysteresis loop in this first round of samples because there was some residual ferromagnetism. So it turns out that if you make a more symmetric device or a more symmetric stack, imagining putting a platinum layer on the bottom, you can eliminate this sort of residual ferromagnetism. This is the magnetization versus field for a tetralayer. So at 1.25 nanometers, you again see ferromagnetic behavior. And what we were looking for was this S-shaped curve when you have 4 layers that has no magnetization when the field is 0. This is a curve that's in agreement with the Macrospin model. You can calculate with the Macrospin model the static equilibrium of each of the moments as a function of magnetic field. So you can basically figure out how the magnetic moments are rotating as you increase the field to come up with a magnetization versus field. And because the surface layers are rotating at different rates than the interior layers as you increase the field, you don't see like necessarily a straight line. You kind of have this nice S-shaped curve. So we were really happy to see this because we think that we have a tetralayer then that is agreeing with the Macrospin model. So just over the last few months, we started to measure antiferromagnetic resonance in these tetralayers. This is just a cartoon of what our experimental setup looks like. We have an electromagnet, and we place the sample on a sample holder that gets put between the poles of the electromagnets. So we have some coaxial SMA cables as an input. It's connected to a signal generator. So we can say use frequencies of 1 to 25 gigahertz. The output SMA line is attached to a microwave diode, and we connect that through BNC to a lock-in amplifier. And we are able to use lock-in detection because as we sweep the magnetic field externally, we have Helmholtz coils that are wrapped around our electromagnetic poles, and we apply a modulation field at around 101 hertz to create an AC signal that the lock-in is able to see. So it just honestly improves signal to noise. This is a well-known field modulation technique that's used in ferromagnetic resonance research. Our sample is placed on a coplanar waveguide, so like this ground signal, ground planar structure. The oscillating field from the signal generator tends to be perpendicular to the length of the signal generator. Sorry, the length of the signal line, and we apply an external field and sweep it and look for absorption of the microwaves as a function of our swept magnetic field. So when we sweep the magnetic field such that it is perpendicular to the RF field, and we scan the frequencies from 2 to 10 gigahertz, this is the spectrum we observe. I apologize that there's no scale bar. This is actually really fresh. So the contour that you're seeing, the dark kind of bright line, is the acoustic antiferromagnetic resonance branch evolving as you increase the field. And it's symmetric. It doesn't matter if you apply a negative field or a positive field, the resonant frequency is at the same value. What we were really happy to see is that there's a break in the acoustic antiferromagnetic resonance line. So it doesn't look like a continuous line. We think that this is the avoided energy level crossing between the two acoustic antiferromagnetic magnons.
Sure, it would be great if we can wrap up in
Okay,
3 minutes.
3 minutes? Okay, then I will be good. Okay, so we've started to measure other configurations, and this was this is where we rotate the magnetic field to be along the direction of the RF field. This should couple to optical antiferromagnetic magnons. We're a little perplexed by this at the moment. You can kind of see the optical branch. It's this downward curving branch at higher fields, but we're still strongly coupling to apparently the acoustic antiferromagnetic modes in the spectrum. And we initially thought that maybe it's because the sample is hanging out over top of the signal line and the region between the ground line and the signal line where the RF field is maybe not necessarily in the plane, but has an out of plane component. So we've started to do things like reposition the sample on the waveguide, and this has led to a quite dramatic effect. So if we create thinner specimens that can fit between the signal line and the ground line, when we are in the acoustic configuration, that's the panel on the far left. The branches, the linear branches are kind of faint to see, but this red bright region that you're looking at, we think is the avoided energy level crossing between the acoustic Magnon modes, and we're not really strongly coupling to them. But what we are now starting to observe when we rotate the field, say 45 degrees from the signal line or perpendicular to the signal line, are more complex spectra than we originally anticipated. We do think, and I'm not sure if my laser pointer will work, we do think that there is a middle branch here, maybe, that is corresponding to a new or one of the optical magnons, but it looks like we're still coupling to these acoustic modes, and we don't know what's happening in this region here. It looks like there's some avoided energy level crossing, honestly, that we can't yet explain. But this acoustic avoided energy level crossing seems to be missing when we're in this optical configuration. So this is a bit of a mystery to us, and these results are days old. One thing that we're thinking about is whether or not we have some ferromagnetic magnon that is in the system that is also coupling to an antiferromagnetic magnon, because our system is assuming, our models are assuming all the magnetic moments are compensated. So I'll just summarize these initial experimental results. We've observed self-hybridization between the acoustic magnons. That's kind of as expected by theory. The optical magnons are present, but we're having a hard time separating them from the acoustic modes. And we're starting current biasing experiments too, where we're trying to modulate the damping on the surface layers to electrically control these interactions. Okay, so I know I ran long. Yeah. I'd like to just also flash up this acknowledgement slide. So the synthesis and characterization of these materials is happening at Wayne State. I have two students, Mitra and Teresa, who you see on the right, who are working on this project. We're collaborating with nearby Oakland University, a longtime friend of mine, Zhang, who's helping us out with some of the microwave spectroscopy early on. And we have a new MPMS that's going to be coming to Wayne State to do magnetometry, but with some of these early, with some of these early magnetometry measurements, we've had some help from John Heron at Michigan to characterize our films. So thank you. I appreciate your time.
Thank you. We can take a few quick questions. Any questions? Catherine? Hi.
You were very beautifully explaining how you incorporated nearest neighbor interactions in your four-layer structure. Can you give an idea of how strong you would expect next nearest neighbor interactions to be? Might they be totally unimportant, or?
It's a good question. We're totally leaving them out of any model, both macrospin or micromagnetic. Based on the experimental reports that are out there from characterizing antiferromagnetic resonance in these materials, it does not seem to be necessary to explain the data. I don't know if there's been so the Curie temperature of these materials and the Nile temperature of these materials, those two temperature points are well known. And I don't know if there's any good theoretical model out there that explains like those two temperatures in terms of just the intralayer and the single interlayer interaction. But I think that, so I'm trying to be careful here in saying that those beyond nearest neighbor interactions are excluded for good reason. I think you can explain the magnetic ordering with just the interlayer antiferromagnetic interaction and the interlayer ferro. So I'm not aware of at least any experimental result that's incompatible with just models that simply use those two interactions. But I will say that it's really easy for us, especially in micromagnetics, to add however many interactions we want. We can slice and dice things up in a couple different regions. And we are starting to see things that are a little unusual, to be honest, in the synthetics. And that might be a direction that we have to head to help explain things. But it's a good question.
So you talked about doing 4 layers, 6 layers, 8 layers. What if you take an odd number of layers? Does anything interesting happen there?
Yeah, so I have a really good high school student who I have working on the Macrospin model for tri-layers. So I think that you have a ferromagnetic resonance if you have an odd number of layers, like something that looks like a Cattell mode. And so I think the odd number of layers are interesting if you want a model system to look at ferromagnetic Magnon, antiferromagnetic Magnon interactions. So we haven't grown them yet. And it's still like an interesting sort of math problem to solve to write the equations of motion. So I'm hoping that this talented student who she's got some advanced math under her belt. So we're thinking about it. And it's easy for us to grow it, honestly. So it's just a matter of bandwidth.
Jesse has a question from Zoom.
Yeah, let me,
The volume.
Yeah, can you hear me?
yeah, I can hear you, Jesse.
Cool, thanks for the talk. If I understand correctly, then all of the FMR modes you're showing, or antiferromagnetic resonance modes you're showing, are like the sort of like K = 0 magnons.
Yes.
So I was wondering what happens at non-zero K, and like when you get to hybridization in particular, does it actually is there a gap at all Ks in that range, or are there other Ks that exist within that gap?
Yeah. While I skip to this slide, I'm not sure if I'm aware of a model where magnetostatic spin waves are derived in synthetic antiferromagnets to explain long wavelength excitations. This experiment here was coupling to these finite wave number optical and acoustic magnons. And to be honest, the scale bar, I apologize, it's missing. I think that we're probably dealing with wave numbers corresponding to wavelengths of tens of microns. It doesn't change the resonant frequency that much. This work here couples to K = 0 and K not equal to 0 Magnon excitations. And the frequencies are very similar. But if you're familiar with like ferromagnetic systems, magnetostatic spin waves don't necessarily have frequencies at long wavelengths that are too different from the FMR. But there are dipolar interactions between finite wave number spin waves in these synthetic antiferromagnets that are coupling the optical to the acoustic modes that are not able to couple the optical and acoustic modes when the wave number is 0. So the coupling is definitely wave number dependent. I guess the overall total coupling between these modes. I'm not aware of a model though, like if you're familiar with Damon-Eschbach spin waves and thin films, I'm not sure, and maybe Shulei can answer if there's been like a rigorous model of spin wave dispersion and antiferromagnet slabs that are coupled together. But experimentally, the frequencies look very similar.
Okay.
Did I answer your question, Jesse?
Yeah, thanks. I'm interested to know more in the future.
Yeah.
Okay, any other question? Yeah,
Okay.
So can we go to the slide on the antiferro and on the artificial antiferromagnet, the cold iron boron?
Yeah.
Yeah, so my first question was, so in the antiferromagnetic phase, the two cold iron boron layers, they're the two self-lattices, right?
Yeah.
So is there a reason they have to be the same?
That the materials have to be the same?
Yeah.
No, you can definitely imagine doing a synthetic ferromagnet. And I know that people, our friends at Delaware, are interested in that. So you can make different thicknesses. That's one way to like sort of have an uncompensated magnetic moment with antiferromagnetic coupling, or you can do two different materials. And that's also sort of an interesting system to study. So yeah, it's easy for us to, we just haven't gotten there yet with the tetra layers. But I would say that if you start to think in that direction, you're making artificial ferromagnets.
2 minutes, we're running a little late, so I suggest to discuss this after the seminar. All right, let's thank our speaker again. For the interesting homecoming talk.
Yes.
Good.
Not too far away from here, huh?
I know, it's nice.